In the presentation you're about to see, we're going to examine the level of protection provided by minimum quantity distance separations for important Air Force Base facilities. These facilities include those that directly support explosives operations, or the servicing, launching, and flying of combat aircraft. We'll also see how increasing the distance between such base facilities and an explosives location will provide greater protection to personnel and increase survivability of operations in wartime. But first, what is QD? Simply put, it is a mathematically defined level of protection based on the relationship between the quantity of explosives and the distance to an exposed site. The history of modern U.S. QD standards goes back more than 60 years to the 1926 disaster at the Lake Denmark Naval Ammunition Depot in New Jersey. There, surplus World War I munitions, ignited by lightning, exploded and propagated to the nearby Picatinny Arsenal, killing 22 people and injuring 51. Political aftershocks led to the creation of minimum quantity distance separation standards, which are legally binding. They also led to the formation of what is known today as the Department of Defense Explosive Safety Board. One major QD disaster occurred at Ben Wad during the Vietnam War. We still don't know what caused the first explosion. It may have been an accident or an enemy sapper. But in the wartime rush, little consideration was given to QD criteria. The violations of intermagazine separation distance allowed the explosions to go on for days. 27 members of our armed forces lost their lives. There are 4 basic quantity distance categories: inhabited building distance, public traffic route distance, intraline distance, and intermagazine distance. Inhabited building distance is the minimum permissible distance allowed between a quantity of explosives and any building inhabited by the public or used for assembly, both within and outside government establishments. This minimum distance provides a high degree of protection against structural damage from blast wave effects. It does not, however, provide protection against breakage of glass. Public traffic route distance is the minimum permissible distance between an explosive site and public highways or railroad lines. It is 60% of the inhabited building distance. This lesser distance is based on the fact that vehicles are exposed for only limited periods as they pass by an explosive's location. Intraline distance is the minimum permissible distance between an explosive's location and a related facility. We'll examine this distance in detail later in this presentation. Intraline distance provides some compatibility to resume operations after a blast. Finally, there's intermagazine distance. This is the minimum permissible distance between storage magazines and is based on the type of magazine and the quantity of explosive inside. It is designed to prevent propagation of explosions by blast and provides reasonable protection against propagation by fragment impact. To get a clearer idea of how QD works, let's look at a specific example. Let's say we want to build a theater at an Air Force base. Looking in the AFR 127-100 Explosive Safety Regulation, we see that the protection, or K factor, for an inhabited building like a theater is 40. This is normally referred to as K40. Next, it must be determined what quantity of explosives are being stored at the locations near the proposed theater. For purposes of our discussion, let's say that the major explosives hazard is a munition storage igloo permitted to house up to 100,000 pounds of explosive. The formula, then, for figuring the minimum distance the theater is required to be separated from the igloo is determined by multiplying the cube root of the explosive weight by the protection, or K factor. Thus, the theater cannot be built closer than 1,856.8 feet from the munitions igloo. Like the theater, other buildings of public assembly cannot legally be sited inside the inhabited building arc. When an explosion occurs, it projects a blast wave that expands outward from the center of the detonation. This wave is composed of a high-pressure shock front that decays in intensity with distance. When the blast wave hits a structure, the structure is engulfed by the high-pressure shock front. This is known as overpressure. The magnitude and distribution of the overpressure are a function of the type and weight of the explosive, the location of the explosion relative to the structure, and the interaction of the shock front with the ground or structure itself. At inhabited building distance, peak overpressure is rated at 1.2 pounds per square inch above normal atmospheric pressure. Is this really safe? You be the judge. As a point of comparison, average windows shatter at 0.25 psi of overpressure, and at 2.0, doors are blown off their hinges. At 3.5 psi of overpressure, concrete walls are damaged, and exposed aircraft suffer major damage. Although the blast wave is a primary hazard from high explosive detonations at this distance, it is not the only source of destruction. We must also be concerned with fragments, both from the casing of the munition that exploded and from debris generated by buildings, equipment, and the ground. By analyzing data from explosive accidents and tests, the Department of Defense Explosive Safety Board has established a 1,250-foot minimum safety distance around explosives locations to reduce the number of hazardous fragments to an acceptable level. What about the risk to Air Force personnel who work in related facilities at intraline distance, such as munitions control, aircraft debrief, and flying squadron operations? As these facilities are essential for combat operations, they are permitted to be located much closer to explosives locations. The protection factor for such intraline facilities is K18, less than half the protection provided at the inhabited building distance of K40. At some bases, 50% of a combat wing's populace may work at K18. In addition to those mission-essential facilities already mentioned, these include the Maintenance Operations Center, command post, alert facilities, aircraft refueling, and base intelligence. In the immediate aftermath of an explosion, facilities located at K18 can experience peak overpressures of up to 3.5 psi above the normal atmospheric pressure. By itself, this is nearly 3 times the overpressure that cracks rafters of buildings. To compound matters, when the blast wave slams into a wall at K18 that is perpendicular to the wave's direction of travel, it shocks up and increases the pressure by as much as a factor of 2. This equates to 7.0 psi overpressure. If the blast wave strikes a building at an oblique angle of less than 90 degrees, the shock to the front wall will be between 3.5 and 7.0 psi. Under those conditions at K18, personnel inside office buildings or industrial shops are likely to suffer serious injury from flying glass, toppling furniture, falling ceilings and light fixtures, or be slammed to the ground by the force of the blast. Personnel injuries of a serious nature or possible death are likely. Because the density of hazardous fragments increases closer to a detonation, it follows that the probability of unprotected personnel being killed by fragments increases at K18 as well. According to AFR 127-100, K18 does not provide minimum fragment protection. Obviously, K18 separation does not protect personnel from serious injury or death from either blast or fragments. If there is a war and an enemy successfully blows up one of our own explosive sites, the functions that we now consider essential to recover a wing after attack may be effectively destroyed. We could be done in by our own explosive sources on the base. How can this risk be minimized? The single most effective way is to increase the distance between the mission essential facility and the potential explosion site. If essential facilities could be sited at no closer than K30, building damage from explosive effects as well as personnel losses could be reduced. A second option is to decrease the quantity of explosives at the explosives locations. But since this normally correlates to a reduction in mission readiness, it is probably not a realistic option at most bases. A third option is to mitigate the effects of explosions by redesigning, hardening, and reinforcing structures. Our business is air power. To accomplish that mission, we must live with the risks associated with storing and handling that power. Due to the limited land area of many bases, there may be no other choice than to request an exemption from QD minimum separations when constructing new facilities. But if that is your choice, make it with a clear understanding of the risks involved.